Picture the scene. You walk into a restaurant. You sit down and you open the menu. Tonight's specials: grilled wolf steak with rosemary butter, crispy fried eagle wings, bear ribs, slow roasted for 12 hours. And for the truly adventurous, seared tiger medallions, served alongside roasted lion. Just reading it makes your stomach turn, doesn't it? But why? They are all meats. They are all proteins. Many of them are probably delicious if prepared correctly. Yet, something deep inside your brain is screaming that this is fundamentally wrong. Here is the strange part. Walk into any grocery store on earth, and you will find beef, chicken, pork, lamb, fish. These are all herbivores, animals that eat things situated lower on the food chain. The meat aisle is packed with plant eaters. But the predators, the carnivores, the animals that eat other animals, are nowhere to be found. Not because they are illegal, not because they taste bad, they are simply absent. This is not a coincidence, and it is not a cultural preference. It is not even really a choice we made consciously. Humans from every continent, every culture, and every era arrived independently at the exact same conclusion. We do not eat carnivores, or at least we almost never do. And when we do, there is usually a very specific reason, which we will return to later. Now, you might be thinking, all right, we prefer herbivores. Big deal. Maybe predator meat just doesn't taste as good. Maybe it's a bit too tough. Or maybe it's just tradition. But here is the part that will blow your mind. There is a hidden mathematical law governing this choice. A rule so fundamental to how energy flows through ecosystems that it dictates not just what we eat, but how many lions can even exist, why food chains stop where they do, and even why life on Earth looks the way it does. Scientists call it the 10% rule, and it is one of the most elegant yet brutal truths in all of ecology. Think about every meal you have ever eaten, every burger, every chicken wing, every fillet of fish. Behind every butcher counter hides an invisible calculation that has been running for billions of years. An energy equation that shapes the entire living world. And once you see it, you can never unsee it. You will understand why farmers raise millions of cows, but absolutely no one raises tigers. Why there are far more rabbits than wolves. Why predators are rare, expensive, and from an energetic standpoint, a terrible thing to eat. But here is the mystery that makes all of this so fascinating. Humans eat almost everything. We are arguably the least picky species on the planet. We eat insects, we eat plants, we eat fungi. We eat things that would kill most other animals. We have figured out how to make poisonous plants edible. We consume the dairy of other species, which almost no other animal does. We eat raw fish, fermented cabbage, moldy cheese, and we call it fine dining. Our species essentially looked at the entire biological world and said, yes, I will try a bite of that. Except when it comes to predators. That is where we draw the line. Almost every human culture independently decided that eating carnivores was just not worth the trouble. This is no accident. It is not superstition. Our ancestors understood something profound about how nature works, long before anyone knew about ecology, energy pyramids, or trophic levels. So what did they figure out? What is the secret hiding in the math of the food chain? Why does eating a predator violate an invisible rule that eating a cow does not? The answer takes us deep into the fundamental laws of energy, into the economics of evolution, and into the surprising logic of prehistoric humans, who somehow grasped truths about nature that scientists only formally discovered in the 1940s. This is about so much more than just food. It is about understanding why ecosystems are shaped like pyramids, why there is always more prey than predators, why energy becomes so much more expensive the higher you climb, and ultimately why a lion's steak, even if you could get your hands on one, represents one of the most wasteful, impractical, and potentially dangerous meals you could ever choose. By the end of this, you will look at your dinner plate in a completely different way. You will understand the invisible energy tax that every living thing pays. You will know why being at the top of the food chain is both incredible and unbelievably costly. And you will never look at a hamburger the same way again, because that hamburger is not just food. It is proof that your ancestors were far better at math than they ever realized. Before we can understand why humans do not eat predators, we need to talk about something far more fundamental. Something so basic, so universally true, that it dictates not just what you are having for dinner, but the entire architecture of life on Earth. We have to talk about energy. And more specifically, we have to talk about the most unforgiving rule in the universe. Energy always has a cost. Every meal you have ever eaten, every single calorie you have ever consumed, every ounce of fuel that has kept your body moving, all of it comes from the exact same source, the sun. Now that might seem obvious when we talk about vegetables, perhaps even intuitive, for meat coming from a grazing herbivore, but here is what most people fail to realize. That chicken wing you had last night, those salmon fillets in your freezer, that steak you are planning to grill this weekend, every single molecule of it began as sunlight striking a leaf somewhere. The sun is the bank, and everything else is just moving money around, with the universe taking its cut of every transaction. Let me show you how this works. 93 million miles away, the sun burns through nuclear fusion, converting hydrogen into helium and releasing absolutely staggering amounts of energy into the void. A fraction of that energy, a tiny sliver, travels through the vacuum of space and strikes the Earth. Most of it bounces off, warms the atmosphere, or is swallowed by the oceans. But a small portion, maybe 1 or 2%, hits something extraordinary. It hits a plant, and that is where the magic happens. Plants figured out something remarkable, something that took billions of years of evolution to perfect. They can catch sunlight, trap it using molecules of chlorophyll, and use that captive energy to build sugar molecules out of thin air and water. This is photosynthesis, nature's original solar panel technology, and it is the bedrock of everything. Think about it. A blade of grass sitting in a meadow accomplishes a feat that human engineering still cannot efficiently match. It takes the diffuse, low-quality energy of sunlight and spins it into chemical energy, locked safely away in sugars. Those sugar molecules are like batteries, portable energy storage that can be used later, moved around, transformed. Every plant on Earth is fundamentally a living solar farm, quietly weaving sunlight into usable power, hour after hour, day after day. But here is the catch. Photosynthesis is not very efficient. Of all the sunlight that strikes a leaf, only 1 to 2% is actually converted into chemical energy the plant can use. The rest is lost as heat, reflected away, or used for processes that do not create storable energy. So right out of the gate, we are dealing with massive energetic losses. If the sun were a bank account holding $1 million, the plants might capture 10,000. Now, plants do not use all of that captured energy to grow tissues that animals can eat. They have to spend energy just to survive. They grow roots, maintain cellular processes, reproduce, fight off diseases. Perhaps 10% of the energy they manage to pull from the sun is actually stored in plant tissues, like leaves, stems, fruits, and seeds. The rest is simply burned away by the plant's own metabolism. So now we are down to about $1,000 from that original $1 million. This is where the food chain, or as ecologists prefer to call it, the trophic pyramid, begins. Plants occupy the first trophic level. They are the primary producers, the only organisms on Earth that can conjure food energy out of nothing but light. Everything else, every animal, every fungus, every bacterium that cannot photosynthesize, is a consumer. We are all just coasting on the energy that plants manage to steal from the sun. The second trophic level belongs to the herbivores. These are your deer, rabbits, cows, grasshoppers, anything that eats plants directly. And this is where things get truly fascinating, because this is where the universe really starts to demand its tax. Think about it. When a rabbit eats a patch of grass, it does not get to keep all the energy stored in those leaves. Far from it. The vast majority of that plant matter passes right through the rabbit's digestive system without ever being absorbed. Cellulose, the tough structural material that makes up plant cell walls, is incredibly difficult to break down. Rabbits have special adaptations to digest it, but even they cannot extract all the energy. Then there is the energy the rabbit spends just existing. Moving around, keeping its body warm, growing fur, fighting off infections, looking for a mate. All of that requires power. Power that is burned up as heat and lost forever to the cold environment. When you add it all up, when you account for all the energetic leaks from digestion, metabolism, and basic survival, here is what you find. The rabbit only converts about 10% of the plant energy it consumes into actual rabbit mass. Only 10% becomes rabbit meat, rabbit organs, rabbit tissue that could potentially feed something else. The other 90% is gone, burned, excreted, radiated away as body heat. So let us do the math again. That $1 million of sunlight became $10,000 of plant energy. The plant spent 90% on itself, leaving $1,000 of edible leaves. The rabbit ate those leaves and only converted 10% into rabbit mass. We are now down to exactly $100. The losses are staggering. But wait, it gets worse. Because the rabbit is food for something else. A fox, let us say, or a coyote. These are carnivores, predators occupying the third trophic level. And when that fox catches and eats the rabbit, the exact same brutal mathematics apply all over again. The fox's digestive system is not perfectly efficient. Parts of the rabbit pass through undigested. The fox burns immense amounts of energy, hunting, defending its territory, staying warm through the bitter winter. Perhaps 10% of the rabbit's energy actually becomes fox. We have gone from $100 down to 10. This is the 10% rule. At every single step up the food chain, roughly 90% of the energy is simply lost. Only about 10% makes it to the next level. Now, it is not an exact number down to the decimal. Some ecosystems run a little tighter. Others are far more wasteful. But 10% is the golden average ecologists use. And it is this rule, this fundamental constraint imposed by the laws of thermodynamics, that dictates the entire structure of life on Earth. You can watch this play out in any ecosystem. Take an African savanna. You need roughly 10,000 pounds of grass to support 1,000 pounds of zebra. And that 1,000 pounds of zebra can only support about 100 pounds of lion. The pyramid narrows dramatically at every single level because the energy leaks are so massive. There is simply not enough power in the system to support more predators than that. The math absolutely forbids it. This is exactly why predators are always rare compared to their prey. It is not because they are bad at reproducing or just down on their luck. It is because the energetic budget of the universe demands it. For every single lion stalking the savanna, there must be dozens of zebras. For every zebra, there must be thousands of pounds of grass. The pyramid has to be built this way. There is no alternative architecture. And this brings us right back to our original question. This is where you begin to see why you have never found a lion steak at the grocery store. Because if you want to eat a predator, you are trying to eat at the third trophic level. You are eating something that represents only 10% of 10% of the original energy. You are eating the most energetically expensive food in existence. Before we dive deeper into what this means for human food choices, I am curious. Where are you watching this from? What time is it where you are right now? Leave a comment below. I love seeing this community stretch across so many different time zones. All of us exploring these same quiet questions about why the world works the way it does. Because what we are talking about here is not just about dinner. It is about the fundamental architecture of life itself. The sun gives. Plants take and lose most of it. Herbivores take from the plants and lose most of it. Predators take from the herbivores and lose most of it. At every single step, the universe collects its tax. At every level, 90% vanishes into entropy. And humans, sitting at the very top of this pyramid, looking out over all the options, had to make a choice. A choice that would be entirely shaped by this brutal mathematics of energy loss. A choice that would determine not just what we put on our plates, but how we went about building civilization itself. But to truly understand that choice, we have to look closer at what the 10% rule actually means on the ground. We need to see exactly why eating predators is not just unusual. It is mathematically absurd. Let us be brutal about energy. Not the comforting, everything is connected energy talk you hear in traditional nature documentaries. I mean the cold, hard math that decides who lives, who starves, and why there are no lion farms. Imagine 1,000 pounds of grass. Beautiful green blades, actively photosynthesizing, soaking up the hot sunlight on an African savanna. A herd of zebras arrives and eats the whole lot. Every blade, every stem, every leaf. Now here is the question that changes everything. How much zebra do you get out of that? If nature were fair, if energy transfer were perfect, you would get 1,000 pounds of zebra. Grass goes in, zebra comes out. Conservation of mass. Everyone goes home happy. But nature is not fair. Nature is a cosmic accountant with the worst exchange rate in the universe. You get about 100 pounds of zebra. That is it. 10%. So what happened to the other 900 pounds? Where did 90% of your meadow go? It vanished into the most expensive biological process there is, staying alive. Let us follow a single blade of grass through a zebra's digestive tract and watch the energy disappear like money in a casino. First, the zebra has to find the grass. That requires movement. Walking, running, scanning the horizon, sprinting away from lions that have not eaten in a week. Every single step burns power. Every muscle contraction converts chemical energy into motion and into heat. A lot of heat. Then comes the chewing. Zebras are constantly eating because grass is incredibly tough to break down. Those heavy jaw muscles work hour after hour, grinding tough plant matter into a digestible pulp. More energy lost, more heat bleeding off into the African air. The grass now moves into the digestive system, and this is where things get truly expensive. Breaking apart cellulose, the rigid structural armor of plant cells, requires a massive investment. Zebras cannot actually digest cellulose on their own. Nothing really can. They need the help of billions of bacteria living inside their gut. These microbes break down the tough fibers, but they do not do it for free. They take their cut, a big cut. They burn a massive portion of that energy just to fuel their own reproduction and metabolism. The nutrients that finally get absorbed have already been taxed several times over. The zebra's cells grab whatever they can and convert it into useful molecules. ATP, the currency of cellular energy. But this conversion process itself is leaky. Energy is lost as heat. Always heat. The second law of thermodynamics does not make exceptions for zebras. Then comes the daily maintenance. The zebra has to keep its internal body temperature hovering right around 100 degrees Fahrenheit in an environment that swings from freezing nights to blistering days. That is brutally expensive. Every single degree of difference between the zebra and the air around it represents energy constantly bleeding away. The zebra is a furnace that can never, ever stop burning. Its immune system demands energy to fight off parasites, bacteria, and viruses, all those microscopic assassins trying to make a home inside it. Its nervous system needs power to process sensory information, coordinate movement, and react to shadows in the grass. Its heart needs energy to pump blood through miles of vessels. Its kidneys need energy to filter waste. Its liver needs energy to detoxify compounds. Every cellular process, every chemical reaction, every waking moment of existence burns through the power pulled from that grass. And the vast majority of it just becomes heat. Always heat, radiating out into the environment, slightly warming the air around the zebra, serving absolutely no biological purpose other than paying the inescapable tax of being alive. By the time the zebra builds some new muscle, repairs damaged tissue, or stores a little fat for the dry season, maybe 10% of the energy from the original grass remains locked inside its body. The rest is gone, burned, lost, turned into the entropy the universe demands as payment for every biological transaction. Now a lion comes along, kills the zebra, eats 100 pounds of zebra meat, and the exact same unforgiving math plays out all over again. The lion might get 10 pounds of new lion out of the deal. The rest vanishes into heat, movement, digestion. The constant crushing burden of staying alive in a body that never stops breaking down and constantly demands repairs. This is the 10% rule. And it is not really a rule so much as a rough average describing the heaviest constraint on life in the universe. Energy flows through ecosystems like water through a strainer. where the holes get bigger at every level. By the time you reach the third level of consumption, predators eating predators, you are down to 1% of the original energy. At the fourth level, you are at 0.1%. Ecologists call this the energy pyramid. It is exactly what it sounds like, a pyramid with producers, plants, and photosynthetic life forming the massive base. Herbivores in the middle and carnivores sitting at the very top. Each level is roughly 1/10 the size of the one below it. Not because of some mystical balance of nature, but because basic physics makes any other arrangement entirely impossible. The discovery of this principle transformed ecology from a descriptive science into a predictive one. The breakthrough came in 1942, thanks to an ecologist named Raymond Lindemann. He was studying a small lake in Minnesota, carefully tracking the flow of energy between different organisms. The plants, the zooplankton, the small fish, and the larger fish. What he found was a remarkably consistent efficiency across the different levels. Roughly 10% of the energy was transferring from one tier to the next. Lindemann died tragically young, at 27, shortly after publishing his findings. He did not live to see his work revolutionize the field. But his paper, The Trophic Dynamic Aspect of Ecology, handed scientists the key to understanding why ecosystems look the way they do, why predators are always rare compared to their prey, why food chains rarely stretch beyond 4 or 5 links, and why the sheer weight of all the plants on Earth vastly outnumbers the weight of all the animals. However, that 10% figure is not carved in stone. It is an average that hides some fascinating variations. Some transfers are far more efficient, hitting 20%. Others are dismal, dropping to 5% or less. The efficiency depends heavily on what is being eaten and who is doing the eating. Cold-blooded animals are generally much better at this than warm-blooded ones. A snake might convert 30 to 40% of its meal into body mass because it is not wasting precious calories trying to maintain a constant internal temperature. It just sits there, occasionally moving, occasionally digesting, going weeks between meals. For a snake, being alive is relatively cheap, but warm-blooded animals, mammals, and birds pay a massive premium for the privilege of staying warm. A mouse might only convert 2 to 3% of its food into growth, because it is constantly burning through fuel just to keep its tiny body at mammalian operating temperatures. Small, warm-blooded animals are catastrophically inefficient. They are essentially tiny furnaces on legs, burning through resources at ridiculous rates just to avoid freezing to death. This is exactly why most of the predators early humans encountered were warm-blooded mammals, just like us. And it is why eating them makes even less economic sense than the basic 10% rule suggests. A lion is not just one step higher on the energetic ladder. It is one step higher on the most inefficient version of that ladder. The energy locked inside lion meat represents maybe 1 or 2% of the energy that was in the plants that fed the zebras that fed the lion. To get 1 single pound of lion, you have to grow roughly 5,100 pounds of plant matter. Compare that to getting 1 pound of zebra, which only costs you about 10 pounds of plants. The math is brutal, and it does not forgive. But it gets even harder. The 10% rule does not just govern how energy moves between species. It dictates how entire landscapes function. It decides how many lions a savanna can hold, how much territory a predator needs to patrol, and how long they can survive between meals. A single lion requires a hunting territory of 20 square miles or more. Not because lions are inherently greedy about real estate, but because physics demands it. There is simply not enough energy concentrated in the prey populations to support more lions in a smaller space. This is why predators spend so much of their lives doing absolutely nothing. Lions sleep for 20 hours a day. They are not lazy. They are being energetically defensive. Every hour spent doing something burns through their precious hard-won reserves. Reserves that are strictly limited by the cold math of energy transfer. When a lion finally does hunt, it is a calculated gamble. The energetic cost of the chase, the sprint, the struggle, the risk of a broken jaw or a shattered rib could easily exceed the calories gained from the kill, if the hunt goes wrong. And lions only succeed in about 30% of their hunts. The other 70% is pure, unrecoverable energy loss. It is no wonder they only run when they are truly hungry. The 10% rule also perfectly explains why apex predators are so incredibly vulnerable to extinction. They sit at the very tip of the energy pyramid, propped up by a massive foundation of plants and herbivores. Mess with that foundation, cut the herbivore population in half, and you do not just cut the predators in half. You might wipe them out completely. There is no buffer, no safety net. The energy available at the top of the pyramid is already hovering at the absolute bare minimum required to keep those predators breathing and breeding. This is the unyielding math that governs every ecosystem on Earth, from the smallest pond to the widest ocean, from the dripping rainforest to the freezing Arctic tundra. The 10% rule dictates what lives, how many can live, and what they are allowed to eat. It is not a suggestion. It is not a guideline. It is thermodynamics, and you cannot negotiate with thermodynamics. These exact, brutal calculations are why your ancestors looked at predator meat and decided it just was not worth the trouble. But to fully grasp why they made that choice, and why we are still living with the echoes of it today, we have to look closer at what it actually means to be a predator in a 10% world. Because the math only gets darker from here. So here is where things get truly profound. This 10% rule we have been talking about, it does not just make raising and eating carnivores energetically foolish. It creates what ecologists call the predator's curse, a fundamental bottleneck that shapes every single environment on Earth. Let us do some quick energy accounting. Imagine you wanted 1 pound of lion meat. Not that you could legally get it, but stay with me here. That 1 pound of lion required the lion to eat roughly 10 pounds of antelope. Those 10 pounds of antelope required the antelope to eat roughly 100 pounds of grass. So your 1 pound of lion meat represents 100 pounds of grass, filtered through 2 highly destructive stages of energy transfer. Now compare that to just getting a pound of antelope meat directly. That only cost you 10 pounds of grass. Same nutritional value for you. 1/10 the primary production required from the land. From a purely energetic standpoint, eating the lion is burning through 10 times more of the ecosystem's solar budget for the exact same result. But here is what makes this truly staggering. It is not just about what is efficient for you to eat. This energy bottleneck dictates how many predators can even exist in the first place. Think about the Serengeti. That vast African grassland supports something like 300,000 wildebeest, 200,000 zebras, 500,000 gazelles. Millions of large herbivores, massive herds, stretching all the way to the horizon during the migration. Do you know how many lions that exact same ecosystem supports? About 3,000. That is it. 3,000 lions, trying to scratch out a living on millions of plant eaters. And it has to be that way. There simply is not enough power flowing through the system to keep more predators alive. If the lion population suddenly doubled, they would not just find twice as much food. They would simply crash twice as hard when they drain their prey base. This creates what biologists call a pyramid of biomass. At the bottom, you have an overwhelming sheer weight of plant matter. Tons and tons of grass blanketing the earth. One step up, you have a smaller total weight of herbivores, maybe 10% of that mass. One step higher, an even tinier sliver of predator mass, maybe 10% of the herbivores. The pyramid squeezes tighter and tighter the higher you climb, not because of some cosmic preference for greenery, but because of raw thermodynamics. The energy lost as heat at every single step leaves less and less fuel available to build bodies on the next level up. You can actually measure this in the wild. In a typical prairie ecosystem, you might find 1,000 kilograms of plant mass per acre. That supports maybe 100 kilograms of grazing herbivores, which in turn might support 10 kilograms of predators. The exact numbers shift depending on the climate and the specific animals involved, but the pattern holds true everywhere. The higher you climb, the less life the system can carry. That is why apex predators are always rare. Not sometimes, not just rare because humans hunted them or paved over their habitats, though we certainly did not help. They are fundamentally, intrinsically rare because reality offers no other option. The universe's energy tax makes it mathematically impossible for predators to be common. Lions, tigers, wolves, bears, killer whales, great white sharks, eagles. Every apex predator you can name exists in tiny numbers compared to their prey. They have to. Their lifestyle is so energetically expensive that only a handful of individuals can afford the rent in any given area. And here is where it gets dangerous for them. These small population sizes make predators incredibly fragile. One bad drought that starves out the grazing animals and the predator populations collapse overnight. They cannot just eat a little less and wait it out. They need massive territories and constant successful kills just to break even energetically. When the prey numbers dip, the predators do not just thin out, they shatter. We saw this happen in Yellowstone after wolves were wiped out in the 1920s. Without the pressure of predators, the elk population exploded, chewed the landscape down to the dirt, and then starved when they ran out of food. When wolves were finally brought back in 1995, the ecosystem slowly started to heal. But it took decades. The wolves could not just show up and instantly build stable packs. They had to negotiate with the energy constraints, growing their numbers at a crawl, while the prey base recovered and the willows grew back. Now there are some fascinating exceptions to the pyramid rule. If you look at aquatic ecosystems, especially out in the open ocean, you sometimes see what looks like an upside-down pyramid. More weight in predators than there is in the prey supporting them. How is that possible? Does the ocean get to ignore thermodynamics? Not quite. It just requires us to look at time differently. In the ocean, the primary producers are phytoplankton, microscopic algae that bloom and die in a matter of days or weeks. The zooplankton that eat them are also tiny and short-lived. But the predators that eat them, and the larger fish that eat those, might live for years or decades, slowly hoarding mass. If you take a snapshot on any given Tuesday, you might weigh more fish than algae. But if you measure the actual production over time, the energy flow perfectly obeys the 10% rule. The phytoplankton are constantly churning out vastly more total life than the fish. They just cycle through it so fast you never catch it all at once. It is like comparing a savings account to a paycheck. Your bank balance might say $10,000, but your annual income is $50,000. The flow of money is huge, even if the standing balance looks completely different. Ocean ecosystems work the exact same way. Production matters more than standing weight when you are tracking the flow of power. But back on solid ground, where humans are trying to figure out what to have for dinner, the standard pyramid rules everything. And it creates some fascinating side effects. Predator populations do not just need energy to survive, they need space. Because their food is scattered across the landscape, predators require enormous tracts of land just to find a meal. A single male lion needs about 8 square miles of territory. A breeding pride might claim 40 square miles or more. Wolves need even wilder expanses, sometimes pushing 1,000 square miles for a single pack in places where prey is scarce. These are not lifestyle choices. They are direct consequences of energy math. Spread the prey out, and the predators have to spread themselves even thinner just to stay alive. This spatial constraint stacks right on top of the energetic one. Even if by some miracle there was enough energy to support more predators, there simply is not enough room. Pack them too tightly, and they spend all their time fighting each other over hunting grounds, instead of actually hunting. In fact, that is exactly what happens when predator numbers temporarily spike. Territorial wars break out. The weaker animals get pushed into the badlands, and the population ruthlessly edits itself back down to whatever the energy flow can sustainably afford. Your prehistoric ancestors understood this in their bones. They lived inside these ecosystems. They watched the predator and prey populations swell and crash. And over generations of silent observation, they learned which animals were common enough to rely on and which ones were just too rare to bother with. They did not need a textbook on ecology to realize that hunting lions was a fool's errand. Lions were incredibly hard to find, deeply dangerous to corner, and tasted no better than the thousands of antelope grazing right next to them. But they would have noticed something else, too. Something that made the choice even starker. Predators were not just rare. They were often actively dangerous to eat, even if you did manage to kill one. And this is where our story takes an even darker turn into the realm of toxins, parasites, and the hidden chemistry of the food chain. But we will get to that shortly. For now, just remember this. The predator's curse is not bad luck, and it is not an evolutionary flaw. It is just math. Every ecosystem on Earth runs on a strict energy allowance handed down by the sun. That energy is taxed at 90% at every step up the ladder. By the time you reach the apex predators, there is so little power left that only a scattering of individuals can survive. They are rare because the universe insists upon it. And that rarity, combined with the staggering energetic cost of building their bodies, makes them terrible candidates for human food. Unless, of course, you are perfectly willing to burn through 10 times more of the Earth's solar budget for the exact same nutritional payoff. A deal that our ancestors, in their quiet wisdom, flatly refused to take. Picture yourself 40,000 years ago. You are standing at the edge of a sweeping grassland in what is now the American West. The sun is just breaching the horizon, frost clinging to the soil. Your breath hangs in the bitter morning air. You are hungry. Your family is hungry. And you have to make a choice that could mean the difference between eating tonight or shivering through another empty dark. You have options. Through the mist, you spot a small herd of elk about half a mile out. 6 or 7 of them grazing quietly, completely unaware you are there. They are heavy, maybe 300 pounds of muscle and fat each. If you can bring just one down, your mouth waters just thinking about it. But then you hear something else. A sharp, distant howl. Wolves. A pack of them, judging by the chorus. And where there are wolves, there might be a fresh kill you could scavenge. Or you could hunt the wolves themselves. It is meat, after all. Protein and calories your people desperately need. So what do you do? Which gamble offers you the best odds of waking up tomorrow? This is not a hypothetical scenario. Your ancestors stood at this exact crossroads thousands of times. And the choice they made, the relentless pattern of decisions repeated across millennia, shaped not only what we put on our plates today, but how we understand food at the deepest possible level. Let us run the numbers the way your prehistoric brain would have. Not with math, obviously. Your ancestors were not drawing up spreadsheets. But with a kind of gut-level cost-benefit analysis, sharpened by hundreds of thousands of years of natural selection. Option 1. The elk. These are herbivores, which makes them relatively predictable. They move in herds, following seasonal rhythms your people have tracked for generations. Their heads are down, focused on the grass, which means they are slightly less paranoid about threats. Most importantly, there are a lot of them. Where you find one herd, you usually find another. If you miss your throw today, you can try again tomorrow. The risks. Elk are fast, and they can be lethal if backed into a corner. Those antlers are not for show. But your people have been hunting them for tens of thousands of years. You know their habits. You know where they drink, where they bed down, how they bolt when spooked. You have tactics that work, driving them toward a cliff edge, isolating a straggler waiting in ambush along their migration routes. The success rate is not perfect. Maybe you only bring one down every 5 tries. But when you do, you feed your entire family for days. Now option 2, the wolves. These are predators, and that changes the entire equation. They are hyper-alert, constantly reading the wind for danger, because they live in a world where a moment of distraction means death. They are brilliantly social, communicating in complex ways, hunting as a coordinated unit. They are fast, they are aggressive, and they are armed with jaws designed to crush the bones of animals much larger than you. But let us say you are a master hunter. Let us say you have a perfectly balanced spear and the nerve to face down a wolf. What is your prize? A full-grown wolf might weigh 80 pounds, less than a third of an elk, and that is total body weight. You cannot eat all of it. You are looking at maybe 30 pounds of usable meat, if you are lucky. Compared to the elk, it is practically a snack, and the math just keeps getting worse. Wolves are incredibly rare compared to the grazing herds. That is just ecology, the 10% rule we talked about earlier. For every single wolf patrolling that valley, there might be dozens of elk. So not only is the wolf vastly more dangerous to hunt and offering far less meat, it is exponentially harder to even find in the first place. And we have not even really talked about the danger yet. Hunting a wolf means willingly walking into a fight with an animal built exclusively for killing. Even if you win, even if your spear strikes true, you might get hurt in the chaos. A bite to the leg, a deep scratch on your arm. In a world without antibiotics, an infected wound is a slow, agonizing death sentence. Is 30 pounds of tough meat worth betting your life when there are 300 pounds of elk standing right over there? Your ancestors were not fools. They felt this calculus in their bones. And we know exactly which path they took because they left the receipts scattered all over the earth. Archaeological sites from Europe to Africa, from Asia to the Americas, all whisper the exact same story. The bone piles outside ancient human campfires are overwhelmingly, undeniably stacked with herbivores: elk, bison, wild horses, deer, antelope, wild sheep. Site after site, continent after continent, the pattern holds. Early humans killed and ate the plant-eaters, not the meat-eaters. At some camps, we find almost zero carnivore bones. At others, we do find the remains of predators, but the cut marks on the bones tell a different story. The herbivores were butchered methodically, every scrap of meat stripped away, the bones shattered to get at the rich marrow inside. The carnivores, they were usually just skinned. The thick fur was a matter of survival. The meat was left to rot. There are exceptions, and we will get to those. But the overwhelming, undeniable trend is clear. Human hunters pointed their spears at the herbivores, and this strategy held firm across wildly different landscapes and cultures. Up in the freezing north, Paleolithic hunters tracked mammoth, caribou, and musk ox. Down in the temperate forests, they stalked deer and wild boar. Out on the sweeping plains, they ran down bison and antelope. Even when they pushed out to the coastlines, they focused on seals and sea lions. Marine mammals that crucially eat lower down on the ocean's food chain, swallowing fish and krill rather than hunting other apex predators. This convergent behavior across entirely separate human populations is stunning. People who never met, who lived in radically different climates, all independently arrived at the exact same conclusion. Do not waste your time chasing the predators when there are perfectly good herbivores standing right there. But why? We have talked about the energy math, but there was another reality ancient humans grasped intuitively. Opportunity. Herbivores are everywhere because plants are everywhere. A landscape can simply hold vastly more plant-eaters than meat-eaters. Walk through a prehistoric forest or prairie, and you would constantly trip over the signs of herbivores. Tracks, droppings, chewed bark, trampled grass. The evidence was everywhere. You did not have to search for them. You naturally bumped into them because they were living in the same spaces, foraging for the same plants your people were gathering. Predators, on the other hand, are ghosts. They have to be. Their entire survival depends on not being seen until it is too late. They are spread impossibly thin across massive territories. A wolf pack might patrol 50 square miles. A lion pride might claim 100. That means you could walk for days without ever laying eyes on a single predator, while passing dozens of grazing herds along the way. So even before you factor in the deadly risks or the pathetic calorie payoff, hunting predators was just bad logistics. They simply were not there to be hunted. The opportunity was not there. But humans being humans, we were adaptable, opportunistic, and sometimes desperation changed the math. In the brutal extremes of the Arctic, where plant life was basically a rumor, and herbivore populations vanished during the long, dark winters, Humans did hunt carnivores more regularly. Polar bears, Arctic foxes, sometimes even wolves ended up over the fire. But look at the context. They were not hunting predators because it was a brilliant strategy. They were hunting them because the better options had disappeared into the snow. Some coastal cultures developed traditions of eating shark, a true apex predator. But they were not usually launching massive expeditions to hunt them down. They took the sharks that wandered too close to shore, the ones that tangled in the fishing nets, the ones that washed up on the beach. It was low-risk opportunism, not a systematic war on the top of the food chain. In parts of Asia, tigers and leopards were occasionally killed and eaten. But this was almost always defensive, or an act of retribution. You killed the predator that was stalking your livestock or threatening your village, and then you ate it, because wasting protein in the ancient world was a sin. Not because big cat meat was a delicacy, but because throwing away calories was unthinkable. The pattern holds true. Even when humans did eat predators, it was situational, opportunistic, driven by defense or desperation. It was never the primary plan. And that makes perfect sense when you remember what your ancestors were actually trying to do. They were not hunting for sport or for a change of pace. They were trying to keep their children alive with the absolute minimum amount of risk and the maximum return on their effort. Every hunting trip was a cold calculation. Every choice carried weight. Go after the wolves, and you might spend 3 days tracking shadows, risk a crippling bite to the thigh, and walk back into camp with barely enough stringy meat to justify the calories you burned walking there. Go after the elk, and you are using a tested strategy, facing better odds, and bringing home enough fat and protein to keep the fires burning for a week. Generation after generation, the humans who made the smart bet, the ones who focused on the heavy, abundant, plant-eating prizes, were the ones who survived the winters and passed on their genes. The ones who burned their energy chasing predators went hungry more often, lost more hunters to infection, and slowly faded out of the gene pool. We are the children of the practical ones, the survivors who looked at a wolf and an elk and thought, not a chance. That ancient choice is now wired into our psychology so deeply we do not even notice it. Walk into any butcher shop in the country and you will not see predator meat behind the glass. Not because it is illegal, though sometimes it is, but because nobody wants it. Our ancestors settled this debate 40,000 years ago, and we are still living by their rules. But the story does not end there. The decision to leave the predators alone was not just about saving calories or avoiding a fight. There were dark, invisible dangers hiding inside predator meat that our ancestors could not possibly have understood scientifically, but that they learned to fear through brutal, first-hand experience. And those dangers are just as real today. There is another reason humans instinctively steer clear of predators. A reason that has nothing to do with energy pyramids and everything to do with poison. Not an intentional poison, not a venom or a toxin the animal made itself. I am talking about accumulated poison. Environmental contaminants that gather strength as they climb the food chain, turning apex predators into walking toxic time bombs. Biologists call this bioaccumulation, and it is one of nature's cruelest mathematical tricks. Here is how it works. Imagine a chemical, a pesticide, heavy metals like mercury, industrial runoff, leaks into the environment. Maybe it washes off a field, spills into a river, or drifts from a smokestack. The concentration seems like a joke. Parts per million, parts per billion, barely a trace. It poses absolutely no immediate threat to anything, but then the algae absorb it. Not a lot, just a microscopic drop. But the algae cannot break it down. They cannot flush it out. The toxin just sits there, locked inside their cells. Then the zooplankton eat the algae. Hundreds of algae for every one plankton, each one delivering its tiny payload of poison. The toxin begins to concentrate. Then the small fish eat the plankton. Thousands of plankton per fish. The concentration spikes again. The medium fish eat the small fish. The big fish eat the medium fish. And with every single step up the ladder, the density of the toxin multiplies. By the time you reach the apex predator at the very top, the concentration of that chemical might be 1,000,000 times higher than it was in the water. What started as harmless parts per billion has compounded into parts per thousand. What was completely safe has become lethal. The classic tragic example of this is DDT and the American bald eagle. The crisis that ultimately changed environmental law forever. Back in the 1950s and 60s, DDT was hailed as a miracle pesticide. It wiped out mosquitoes, protected crops, and seemed entirely safe for humans and wildlife. We sprayed it everywhere. The baseline levels in the environment were incredibly low. Nobody blinked an eye. Then the bald eagle populations began to freefall. It was not a direct poisoning. It was something far more insidious. The DDT was bioaccumulating in the eagles' bodies, concentrating with every single fish they pulled from the rivers. And inside the eagles, it did something subtle and devastating. It scrambled their calcium metabolism. The female eagles still laid eggs, but the shells were unnaturally thin. When the mothers sat down to incubate them, the eggs simply crushed under their weight. Entire generations of eagles never hatched. By the early 1970s, there were fewer than 500 nesting pairs of bald eagles left in the lower 48 states. The national symbol of the United States was pushed to the absolute brink of extinction, quietly erased by a chemical that looked perfectly harmless at ground level. But here is the terrifying part. The fish the eagles were eating were not dying. The medium-sized predators eating the smaller fish were mostly fine. Only the apex predators, the ones sitting at the very peak of the food chain, were destroyed. Because it was only inside their bodies that the toxin had compounded enough to break the machinery of life. This exact same principle is why pregnant women are warned away from eating tuna. Not salmon, not sardines, not the little guys. Tuna. Specifically, the massive deep-water hunters like bluefin and albacore. These are the wolves of the sea, and they are loaded with mercury. Not because they swim in highly polluted waters, but because they eat the fish that eat the fish that eat the smaller fish that absorbed trace amounts of mercury from the ocean. By the time that mercury settles into the muscle tissue of a giant tuna, the dose is concentrated enough to damage a developing human nervous system. Your ancestors did not know the word bioaccumulation. They did not have chemistry labs or toxicology reports. But they did not need them. They had something far more unforgiving, thousands of generations of direct observation. When people made a habit of eating predators, some of them got sick. Not always right away, not in ways that made immediate sense. But over time, the patterns emerged. Weakness, trembling, miscarriages, madness. The patterns hardened into rules. The rules hardened into taboos. Do not eat the giant fish. Do not touch the bear's liver. Leave the wolf alone. These were not primitive superstitions. They were hard-won survival strategies encoded into culture because they kept the tribe breathing. The Inuit peoples of the Arctic developed incredibly strict rules around hunting and eating polar bears. They ate the meat carefully, but the liver was absolutely forbidden. Breaking that taboo meant severe, violent illness, and often death. Western explorers had to learn this lesson the hard way. Early Arctic expeditions lost men to polar bear liver poisoning. They suffered from hypervitaminosis A, a toxic, overwhelming overdose of vitamin A that causes your skin to peel off, your liver to fail, neurological collapse, and eventually death. The polar bear's liver was packing away insane amounts of vitamin A because the bear ate seals, which got it from eating fish, which got it from eating smaller fish and crustaceans. Bioaccumulation striking again. But the indigenous people figured it out through generations of painful trial and error, and they locked the solution away inside a cultural taboo. But heavy metals and vitamins are not the only things hiding in predator meat. Parasites absolutely love carnivores. For many parasites, a predator is the grand finale, the ultimate host at the end of a bizarre, multi-species life cycle. Take trichinella, the nasty little roundworm that causes trichinosis. Its absolute favorite real estate is the muscle tissue of meat eaters. Bears, wild boars, big cats. The larvae of this parasite curl up inside the muscle fibers and build little cysts around themselves, just waiting for their host to get eaten by another predator. When that happens, they wake up in the new stomach, reproduce, and send thousands of their offspring drilling into the new host's muscles, waiting for the cycle to continue. When a human eats predator meat, we accidentally step into that nightmare loop. The larvae hatch and bore into human muscle tissue, triggering massive fevers, agonizing muscle pain, and sometimes fatal complications. Historically, getting trichinosis from bear meat was common enough that almost every culture that hunted bears developed incredibly strict rules about cooking it. You roast it slow, you roast it long, and you never ever eat it rare. Because fire is the only thing that breaks the cycle. And then we reach the prions. They are not alive, not really. Just misfolded proteins that act like a microscopic contagion, bumping into healthy proteins and twisting them into the same broken shape. They clump together in nervous tissue, specifically the brain and the spinal cord, and they are disproportionately found in predators and scavengers. Mad cow disease is the famous one, but that was actually a predator's disease forced upon an herbivore when industrial farming started feeding processed animal parts back to cattle. The natural reservoir for prion diseases sits with the carnivores and the scavengers, the animals that crack open skulls and eat the nervous tissue of their prey. Chronic wasting disease in deer and elk. Scrapie in sheep. These exist at low hums in wild populations, and the predators that eat the infected animals slowly hoard those twisted proteins in their own brains. Human populations that practiced ritual cannibalism learned this lesson in the most devastating way possible. The four people of Papua New Guinea suffered through kuru, a terrifying prion disease they contracted by eating the brains of their deceased relatives. It caused a slow, unstoppable neurological unraveling, ending in death. The practice was stopped in the 1960s, but people continued dying of kuru for decades because prion diseases can sit quietly in the brain for 50 years before they strike. This is exactly why almost every single meat-eating culture on Earth has deep, unshakable taboos against eating the brains, the spinal cords, or the eyes of predators. The biological gamble is just too extreme. Even modern food safety laws respect this ancient fear. In countries with a history of prion outbreaks, the nervous tissue of older cattle is strictly banned from the human food supply. The mathematical probability of a twisted protein slipping through is simply too high. And finally, there is the issue of taste. It is the thing no one really talks about, but everyone notices. Predator meat tastes bad. Not just a little different, bad. And there is a chemical reason for it. The strong, pungent, almost metallic flavor of carnivore flesh makes it deeply unappealing compared to a clean cut of venison or beef. Part of this comes down to diet. An animal's flesh tastes like what it eats. Herbivores eat plants, so their fat and muscle tissues carry relatively clean, neutral profiles. But predators eat blood and bone. Their bodies are saturated with the breakdown products of animal protein, urea, ammonia, complex nitrogen compounds. Their fat stores are loaded with fat-soluble chemicals pulled from the bodies of their prey. All of this combines to create a flavor profile that human taste buds recognize on a very primitive level as an alarm bell. Our sense of taste evolved to act as a chemical warning system. Extreme bitterness warns us of plant toxins. Sharp sourness tells us meat is rotting. And that hyper-distinct, overwhelmingly gamey taste of predator meat. It is a biological red flag, signaling that this tissue is loaded with accumulated compounds that might hurt us. The ancestors who took one bite of wolf meat, gagged and threw it to the dogs, were just a tiny bit more likely to survive than the ones who forced it down. Over hundreds of thousands of generations, that slight preference sharpened into an instinct. This is why the few cultures that do regularly eat predators had to invent incredibly elaborate ways to prepare them. Soaking the meat for days to draw out the ammonia, burying it in aggressive marinades, boiling it with antimicrobial herbs to mask the rotting tang. These were not culinary flourishes meant to impress guests. They were survival strategies, cultural workarounds to the biological problem of eating at the top of the food chain. The Sami people of northern Europe, who historically hunted bear, developed multi-day preparation rituals. The meat was aged under strict conditions, soaked in specific brines, and cooked down with herbs known for their medicinal properties. This was not just tradition, it was applied chemistry. Ancient knowledge encoding the safest possible way to dismantle an apex predator. So when you walk down the aisle of a modern grocery store and you see rows of beef, chicken, pork, and lamb, but absolutely no cougar cutlets, no wolf steaks, no bear roasts, you are looking at the cumulative result of millions of years of evolutionary pressure and thousands of years of cultural memory. We leave the predators alone, not just because they are an energetic waste of time, but because they are biologically hazardous in ways our ancestors could not name, but definitely suffered. Every toxin that spills into the world races up the food chain to settle in their flesh. Every parasite uses them as a final destination. Every harsh metallic note in their meat is an ancient warning. All of it adds up to one inescapable conclusion. Predators make terrible food. They are expensive, they are inefficient, and they are genuinely dangerous. And we figured that out long before we knew how to explain why. Imagine a village 10,000 years ago, nestled in a river valley. Mud brick houses, the thin blue smoke of cooking fires rising into the air. Fields of ancient grain just starting to turn golden in the sun. And tethered just outside the village walls, goats. Maybe a few sheep if you are in Asia. Perhaps some rough, heavy cattle that look more like wild aurochs than modern dairy cows. If you are in the Americas, maybe llamas or alpacas. But notice what is missing. There are no cages full of wolves, no holding pens for lions, no cheetahs carefully bred and lined up like racehorses. Across the entire planet, every single time humans made the monumental leap from hunting to farming, we made the exact same foundational choice. We domesticated the herbivores alongside a few opportunistic omnivores. Animals that happily chew on grass leaves, seeds, and scraps. Animals that take low-quality fibrous plant calories and magically upcycle them into meat, milk, and fat. Why? Because long before anyone could write down the words trophic level or the 10% rule, our ancestors were doing the math in blood, sweat, and starvation. Look at the roster of our major domestic animals. It is almost comically one-sided. Cows, sheep, goats, all herbivores. Horses, donkeys, camels. Herbivores drafted for transport, war, and labor. Llamas, alpacas, yaks, water buffalo, herbivores again. Chickens, ducks, geese. Technically omnivores, but they spend their days turning seeds and bugs into edible protein. Pigs, omnivores that happily root through the dirt for tubers, scraps, and anything vaguely edible from fallen acorns to leftover porridge. When humanity decided to bet its entire survival on animal agriculture, we overwhelmingly drafted species from the very bottom of the food chain. We picked the animals that eat the things we cannot digest or do not want to eat, and let them upgrade those calories for us. Now imagine the alternate universe. You walk through that same ancient village, and instead of cattle, there are fenced-in enclosures full of pacing leopards. Packs of domesticated hyenas waiting behind wooden palisades. A crocodile breeding program in the muddy palms next to the wheat fields. It sounds like the setup for a horror movie. But put the obvious physical danger aside for a second and just look at the energy economics. That leopard has to eat something, and it is not going to eat hay. Every predator sits at the peak of a biological pyramid. For a carnivore to gain a single calorie of mass, its prey had to eat about 10 calories. The plants at the absolute bottom had to capture about 100 calories. That is the 10% rule in action. With every link in the chain, 90% of the energy vanishes into heat, motion, waste, and the sheer effort of staying alive. Now take that unyielding logic and apply it to farming. Let us say you have a plot of land that can grow enough plants to capture 100,000 calories of sunlight in a year. If you let cows or goats graze that land, you might walk away with about 10,000 calories of edible meat and milk. It is not perfect. There are leaks and inefficiencies, but it roughly tracks the 10% rule. Now try raising a predator on that exact same land. Your lions, wolves, or crocodiles have to eat herbivores. Those herbivores still only pass on about 10% of their calories. So by the time the lion turns its food into lion flesh, you have lost another entire order of magnitude. From that original 100,000 calories of plant life, you are lucky to get 1,000 calories of lion meat. Same land, same sunlight, 10 times less food. Farm cows, you feed a village. Farm lions, you feed a family. The math is just that brutal. The higher up the food chain you try to farm, the more land, water, and time you burn per edible calorie. You are running your entire food system through a biological shredder, and the problems just keep compounding. To raise a lion, You do not just need plants. You need to build an entire miniature ecosystem full of prey animals, which means you need more fields, more pastures, more water. Multiply that by every predator you want to raise. Very quickly, the sheer acreage you need swells to absurd proportions. In simple terms, if a cow needs a certain amount of pasture to live, a lion that survives on cow-sized prey needs roughly 10 times that amount of plant productivity spread out across its prey base. To truly farm that lion, not just hunt it in the wild, you would have to dedicate staggering tracts of land just to grow the plants, to feed the animals, to feed the lion, to feed you. It is like deciding to power your house with electricity generated by a motor that is plugged into another motor that finally powers your light bulb. You could do it technically, but why on earth would you? Our ancestors did not know the laws of physics, but they knew how to count. They could see that a herd of goats turned useless, scrubby hillsides into milk meat and leather year after year. They could see that if you kept pigs near the house, they turned garbage acorns and crop waste into rich fat and bacon. They could see the birds scratching in the dirt, turning spilled grain and hidden beetles into fresh eggs almost daily. Try doing any of that with a leopard. Yet there are a few carnivores we actually do farm today. They are just not the ones you picture stalking the savannah. Think about salmon, tuna, trout, carnivorous fish. Modern aquaculture frequently raises fish that survive by eating other fish or high-protein feeds. But look closer at the economics of it. For decades, farming carnivorous fish meant grinding up wild-caught fish anchovies, sardines, other small schooling species into fish meal and fish oil. We were taking low-level wild-caught herbivores and omnivores, throwing them into an industrial blender, and feeding them to farmed predators. From an energy perspective, it is the exact same ancient problem. You are compressing a wild marine food web into a pellet, and then burning away most of that energy again as your farmed salmon swims, digests, and grows. This is one of the main reasons traditional carnivorous fish farming has such a heavy environmental footprint. It sits high on the trophic ladder, right where energy is inherently scarce and wildly expensive. It is only through careful modern feed reformulation, swapping out fish meal for plant proteins and insect meal, that we are starting to claw back some efficiency. In other words, even when we do farm carnivores, we are constantly trying to force them down the energy pyramid, feeding them as if they were herbivores in disguise. So why did chickens, pigs, and cattle become the undisputed planetary superstars of meat production? Chickens are tiny feathered energy converters. Give them grain, bugs, and kitchen scraps, and they spin them into eggs and meat at astonishing speed. A single hen can lay hundreds of eggs a year, hundreds of dense, perfect little nutrient packets, built mostly out of seeds and invertebrates that we have no interest in eating. They grow fast, breed quickly, and take up very little space. Energetically, chickens are one of the tightest links you can build between a plant and a human mouth. Pigs are the ultimate recyclers. In traditional farming systems, they act as biological vacuums, sweeping up everything nothing else wants. Potato peels, spoiled grain, the byproducts of brewing beer or making tofu, fallen fruit, even bones. They can thrive on the things that would otherwise just rot. You are not just feeding pigs. You are compressing a waste stream back into usable calories. On an energetic level, that is massive. You are rescuing power that was about to be lost to the void. Cattle, meanwhile, shine on land we simply cannot use for crops. Steep, rocky hillsides, semi-arid plains, freezing, windswept pastures. They eat cellulose, a tough plant fiber we absolutely cannot digest, and they magically transform it into rich protein and fat. In environments where human beings cannot grow, dense fields of grain, herbivores are the only bridge we have. The only way to turn wild, tough plant biomass into something that keeps us alive. This is exactly why pastoralism, the herding of cattle, sheep, and goats, spread across vast, unforgiving stretches of Africa, Asia, and Europe. It was not born out of sentimentality. It was pure, undeniable, energetic logic. And as agriculture scaled up into the industrial age, that same logic stayed firmly in the driver's seat. It just became sharper, harder, and heavily mechanized. Modern feedlots, sprawling broiler sheds, and massive pork facilities are at their core giant machines designed to maximize the transfer of energy from plants to people. We breed the animals to grow faster, pack on more muscle, and convert feed with ruthless efficiency. We engineer their diets so that every possible calorie ends up as edible tissue, rather than being wasted on growing bone, fur, or walking around. We tightly control the temperature, the lighting, the disease vectors. In energetic terms, we are trying to plug every single leak in the system. You can see the shadow of the 10% rule, hiding inside every Excel spreadsheet used by a corporate agribusiness. Feed conversion ratios, growth curves, carcass yields. They do not call it ecology, but it is the exact same equation. How much plant energy goes in? How much edible meat comes out? How much did we lose in the dark along the way? And that brings us to the newest frontier in the long history of domestication: alternative proteins. If herbivores are more efficient than carnivores, what is more efficient than an herbivore? The plants themselves. When you eat a bowl of beans, lentils, or tofu, you are stepping just one rung up from the soil on the energy pyramid. There is no cow or pig standing between you and the sun. The losses are minimal. This is exactly why, calorie for calorie, plant-based diets generally require significantly less land, less water, and less overall energy input than meat-heavy diets. You have simply shortened the chain. Insects offer another strange, highly efficient path. Many insect species are ultra-efficient at turning plant waste or low-value biomass into dense protein. They are small, cold-blooded, and do not waste a single calorie trying to keep themselves warm. In terms of raw energy transfer, a cricket farm looks a lot more like a hyper-efficient herd of grazing herbivores than a pride of lions. Even lab-grown meat, if it ever truly scales up economically, is fundamentally an attempt to bypass the massive energetic waste of running a whole animal. An animal with bones, a brain, an immune system, and a constant need to move. You feed nutrients directly to a vat of cells and ask them to build muscle. No hooves, no horns, no wandering around a pasture burning calories. In theory, you are rewiring the entire energy circuit to cut out as much loss as physically possible. All of these modern experiments, the beans, the bugs, the bioreactors, are really just different ways of asking the exact same ancient question. How do we pull the absolute most edible energy out of the world, using the least amount of land, time, and risk? 10,000 years ago, our ancestors answered that question by throwing ropes around goats instead of leopards. They did not have spreadsheets or ecological modeling software, but they had something far more unforgiving: the brutal, multi-generational test of survival. Any ancient community that stubbornly tried to survive by domesticating predators would have been outcompeted, starved out, or simply erased by the math. The agricultural revolution was not just about taming wild animals. It was about aligning human culture with the hidden arithmetic of the food chain. The herbivores won. The predators lost. Not because we loved cows more than we loved lions, but because the universe demands a punishing energy tax at every step of the ladder. And when your entire civilization depends on exactly how much food you can drag out of a patch of dirt, you do not argue with that tax. You build your entire world around it. So if the 10% rule makes predator meat such a terrible deal, why do some people still eat it anyway? Why are there shark fins on banquet tables in East Asia, bear meat in Siberian stews, crocodile sizzling on grills in parts of Africa and Australia? If eating predators is such a losing strategy, how did these habits survive at all? Because evolution does not care about abstract rules. It cares about what keeps you breathing until tomorrow. And in certain extreme situations, the cost-benefit calculus tilts just enough to push humans back up the food chain. Even if it is just a little bit, even if it is just once in a while. Let us start with one of the most unforgiving places on Earth, the Arctic. Imagine a landscape where plant life barely exists. There are no fields of wheat, no fruit trees, no rolling green pastures, just ice snow and tough lichens clinging to bare rock. Brief flashes of tundra grass during a summer that feels more like a slight pause in the winter than a real season. If you want calories up here, you have to take them from animals. There is no plan B. This is the world of the Inuit and other Arctic peoples. And in this world, the 10% rule still applies. But your options are radically different. You cannot raise cows when there is no grass. You cannot rely on nuts and berries when the growing season is just a few frantic weeks. So they went to where the energy had already gathered. Seals, whales, walruses, and sometimes terrestrial predators like polar bears, massive ocean-fed animals that had already done the impossibly hard work of harvesting sunlight thousands of miles away. Hunter-gatherers in temperate regions could afford to be picky. They could choose the deer and leave the wolves alone. Arctic hunters did not have that luxury. If a polar bear wanders near your camp, it is not just a terrifying threat. It is hundreds of thousands of calories walking on 4 legs. Meat, thick fat, organs, warm, skin, tools, clothing. In a place where one failed hunt can mean a slow, freezing death, letting that walk away would be a form of suicide. But even here in the frozen extremes, notice the pattern. Bears are not an everyday meal. They are rare, highly dangerous, and wrapped in heavy taboos. Many Inuit traditions surround polar bear hunting with intense rituals. Specific people are allowed to eat specific parts. Certain organs are strictly avoided or tossed only to the sled dogs. The deep knowledge of which tissues are toxic, which parasites to watch out for, the safest ways to cook the meat. All of this acts as cultural armor against the severe biological downsides of eating an apex predator. The 10% rule did not vanish in the Arctic. People just found themselves backed into a frozen corner of the world where the normal rules of what is efficient had to bend to what was entirely necessary. Move south into the boreal forests and the mountain ranges, where bears also roam, and you see a slightly different pattern emerge. Siberian hunters, certain Native American groups, rural communities, in parts of Japan and Eastern Europe. Many of them hold traditions of eating bear. Sometimes it is for pure survival during the lean, starving months. Sometimes it is for prestige. Sometimes it is just a side effect of eliminating a heavy competitor that was hunting the same deer you were. Bear meat is incredibly dense in calories, especially the fat, but it comes with a heavy price tag. Parasites like trichinella, bioaccumulated toxins, a wildly unpredictable, gamey taste. In many of these cultures, bear is not the daily staple. It is a rare, risky, often ceremonial meal. It is something you tell stories about around the fire, not something you build a reliable cuisine around. Sharks tell a very similar story, just in a different shade of blue. Imagine navigating for days across the open ocean. No land, no farms. Your calories come from beneath the surface, or they do not come at all. If a massive shark appears beside your boat, you are not looking at an abstract problem of trophic levels. You are looking at food. Muscle-rich liver oil, cartilage, pure energy. Across the Pacific and Indian Oceans, traditional seafaring cultures sometimes ate shark. But again, look closely at the pattern. Shark is usually treated as something distinct, not standard fare. In parts of Polynesia, shark meat was strictly reserved for the highest-ranking chiefs. In Japan, certain shark species were considered a fallback desperation food for impoverished coastal towns. In many Chinese coastal areas, the meat might be eaten when caught, but the fins, the least calorically useful part of the animal, became a towering symbol of wealth and status in shark fin soup. From the perspective of the 10% rule, this is almost darkly funny. The single least efficient source of meat in the entire ocean becomes a prestige dish whose primary function is not to keep you alive, but to signal to everyone else how powerful you are. You do not eat shark fin because it is an energetic bargain. You eat it to prove to the room that you are wealthy enough to afford to waste energy. Modern exotic meat markets have just taken this ancient pattern and stretched it. In high-end restaurants and tourist traps around the globe, you can find lion burgers, crocodile skewers, alligator sausages, snake wine, and even canned tiger meat in certain black markets. They are not feeding the masses. They are feeding something else entirely. The deep human need to feel special, dominant, adventurous. Predator meat survives in the modern world purely as a novelty, a dare, a luxury. The ecological math never went away. We just temporarily insulated ourselves from it, because fossil fuels and industrial farming flooded our world with incredibly cheap, subsidized herbivore calories. When you are surrounded by $5 chickens and endless oceans of beef, you can afford to turn an apex predator into a conversation starter. But there is another group of predators we eat all the time without giving it a second thought and without any of the drama. Think about your last seafood platter. Shrimp, crab, lobster. Maybe a beautiful fillet of cod or wild salmon. In the ocean, almost everything eats something else. Even shrimp, tiny as they are often small predators, vacuuming up worms, microscopic crustaceans, eggs, and larvae. Crabs are opportunistic omnivores, perfectly happy to shred and eat anything they can get their claws on. Cod and many whitefish species are voracious hunters of smaller fish and invertebrates. Salmon spend a huge chunk of their lives as open-water predators, relentlessly chasing down schools of smaller fish. We do not think of them as meat eaters because they are relatively small or because they live underwater. But trophically speaking, a huge section of the seafood aisle sits far above the plants. So why does eating a salmon feel so different from eating a lion steak? Because the ocean's energy pyramid is built on a ridiculously wide foundation. Phytoplankton and algae capture sunlight at a scale that makes terrestrial grasslands look like potted houseplants. These microscopic primary producers feed vast swirling clouds of zooplankton, which feed the small fish, which feed the bigger fish, which eventually feed the salmon and the cod on your plate. The 10% rule still absolutely applies. But when the base of the pyramid is that unimaginably wide, moving a few steps up can still support a massive weight of life. You can have booming, highly productive fisheries of mid-level predators because the baseline productivity of the ocean is so massive and so continuous compared to most land systems. Humans skim off this middle to upper tier, the shrimp, the crabs, the schooling fish, without immediately collapsing the entire food web. If you overfish them long enough, of course, you absolutely will collapse it. But that is a different chapter of the story. Reptiles add yet another fascinating wrinkle. Travel through parts of the American South, and you will find alligator on the menu. Head over to West and Central Africa, and crocodile shows up in the markets. In Southeast Asia, monitor lizards, snakes, and crocs make appearances in traditional dishes. Certain Amazonian groups will happily roast a caiman if the opportunity presents itself. Most of these animals are apex predators, or at least active hunters. Yet here again, they rarely form the absolute backbone of a cuisine. They are utilized as supplemental protein, seasonal windfalls, prestige foods, or simply the thing you eat when nothing else is biting. The taste is often described as somewhere between chicken fish and tough pork. Not exactly mind-blowing enough to override the brutal energetic cost. And hiding in here is another subtle point. In many of these cultures, people are also eating herbivores whenever they possibly can. The presence of crocodile or snake on the menu does not mean these societies rejected the logic of the 10% rule. It usually just means they live in ecosystems where reptiles are highly abundant, relatively easy to trap during certain seasons, or so dangerous that killing them is already a necessary part of staying alive. If you have to kill a massive crocodile because it keeps taking your goats, burning the body would be a tragic waste. Eating it is just closing the loop. So why did none of these predators ever become a global, everyday staple, like the cows, pigs, and chickens that built civilization? It comes down to a handful of unyielding realities stacking on top of each other. First, efficiency. You can domesticate an herbivore, feed it tough, fibrous plants that human stomachs cannot process, and watch it turn that waste into milk, muscle, fertilizer, and plowing power. Try that with a lion or a shark. Predators demand high-quality meat. To raise them at scale, you would have to feed them other animals that you could have just eaten yourself. Every single step up the chain is a massive loss. In a pre-industrial world where every calorie of labor mattered, that is economic suicide. Second, the risk. Predators fight back. They bite, they claw, they maim, and they kill. A species you can herd, milk, and corral is a vastly safer long-term investment than a species that looks at you and sees either a rival or a meal. Herbivores might panic and trample you, sure, but they do not actively stalk you in the dark. Third, disease and toxins. Meat eaters carry a much higher risk of harboring parasites perfectly adapted to mammalian or avian bodies. They sit at the terrifying end of bioaccumulation chains, especially in our polluted modern world. Bears loaded with mercury from fish, sharks packed with heavy metals, large reptiles carrying parasites and chemical ghosts from everything they ever swallowed. Over generations, cultures notice these patterns. This meat makes you sick more often. Those observations harden into taboos, cautionary tales, and religious laws. Fourth, predictability. Herbivores can be penned, bred, and counted. You can plan your harvests around them. Predators are solitary, fiercely territorial, and demand massive ranges. Their populations boom and crash violently, tied to the health of entire, sprawling ecosystems. You cannot build stable, permanent cities on a food supply that vanishes every time the local deer population dips or the fish stocks move offshore. Finally, culture. Once agriculture truly took off, the societies that leaned heavily into domesticating herbivores and planting crops could suddenly support vastly larger, more stable populations. Their cuisines solidified around grains, beans, and the meat of docile animals. Eating predators survived only at the absolute fringes, in extreme climates, on the ragged edge of frontiers, in ritual exceptions, or in luxury markets. It never formed the backbone of an empire. In other words, the exceptions actually prove the rule. When humans eat predators, it is almost always out of sheer necessity, heavy symbolism, or idle curiosity. Not because it is a smart, energetic deal. The 10% rule is always running in the background, quietly dictating what is easy, what is profitable, and what can actually scale. We can defy it for a moment. We can find clever workarounds, or we can turn it into a spectacle for adventurous diners. But build an entire food system on meat eaters. Our ancestors ran the numbers, whether they knew it or not, and walked away. And the closer you look at your plate, at what we eat casually, what we eat only on a dare, and what we never even consider as food, the more you begin to see this invisible arithmetic holding the entire world together. Now take a step back. Forget about humans, predators, grocery stores, and ethics for just a second. Imagine you are looking at the Earth the way an alien ecologist might. No borders, no countries, just glowing, shifting flows of energy. Sunlight strikes the planet. Plants catch a tiny, shimmering fraction of it. Animals eat the plants. Other animals eat those animals. At every single step, roughly 90% of that energy simply evaporates into heat, motion, waste, and the sheer exhausting cost of staying alive. Only about 10% makes it into the next body up the chain. This simple, relentless leak, this constant bleeding away of power, quietly dictates the rules for every living thing. It decides how many predators an ecosystem can hold, how tall the forests can grow, where the deserts form, and exactly how many humans can stand on this planet before the floor gives way beneath us. And it explains why food chains almost always hit a hard, unbreakable ceiling. Think about a classic food chain. Grass, arrow, antelope. Arrow, lion. The grass catches the sunlight. The antelope converts a fraction of that plant energy into muscle and fat. The lion converts a fraction of that antelope into its own body. Every step loses 90% of the original spark. If 10,000 units of energy fall from the sky as sunlight, maybe 1,000 become plant tissue, maybe 100 become antelope meat. only 10 become lion. By the time you have gone plant, herbivore, carnivore, you are already dealing with crumbs. Try adding another level. Say something that eats lions. Now you are down to one single unit of usable energy. You cannot build many bodies with that. Not big bodies, not a stable population. The whole architecture starts to wobble. This is exactly why most real-world food chains do not go on forever. Not because nature lacks imagination, but because the mathematics simply refuse to allow it. On land, you almost never see more than 4 or 5 trophic levels. Plants, plant eaters, mid-level hunters, apex predators, and then the scavengers and decomposers waiting to recycle the scraps. You can stretch it a little further in the deep ocean, where the energy pathways get weird and convoluted. But even there, you eventually hit the exact same wall. The 10% rule. The energy losses compound. Every extra step is another massive tax. And after a few steps, there is simply nothing left to tax. This is why apex predators are always rare. Not sometimes, not usually. Structurally, mathematically, they have to be. There is just not enough power left in the system to support millions of tigers, or oceans boiling with sharks, or endless prairies packed with wolves. For every single lion you see on the savannah, you need thousands of antelope, and for every antelope, you need a rolling carpet of grass. The higher you sit, the thinner the air gets. Now put humans back into the picture. For the vast majority of our history, we behaved like a mixed-feeding omnivore, somewhere in the messy middle of the web. A little hunting, a lot of gathering, scavenging when we could, opportunistically bouncing up and down the chain, depending on our luck and the turning of the seasons. Then something happened that completely shattered the ancient energy logic. We stopped just participating in the food webs, and we started redrawing them. When we invented agriculture, we essentially hacked the 10% rule in a very specific, brilliant way. We did not make the rule disappear. We just started rigging the system so that a much larger share of every 10% slice ended up in our mouths instead of feeding other species. Look at a wheat field from space, or a cornfield, or a rice paddy. What you are looking at is a hijacked ecosystem. A piece of land that could have supported a chaotic, tangled web of plants, bugs, birds, reptiles, and mammals has been stripped down and simplified into 1 or 2 species, plus us. Instead of letting wild herbivores eat those plants, we harvest the plants directly. Instead of letting wild predators eat the herbivores, we become the predator. Or we domesticate the herbivores, lock them up, and eat them later, on our own schedule. Every time we eat plants directly, we act as primary consumers. We are harvesting that first 10% cut straight from the source. Every time we eat beef, pork, or chicken, we are eating one level up, and we pay the 90% energy tax that comes with it. This is why you can feed vastly more humans per acre with grains, beans, and vegetables than you ever could with cows. The 10% rule is not a vegan slogan. It is just physics. When humans figured out farming and scaled it up, we were doing exactly what our ancestors did when they survived that ancient population bottleneck and spread out of Africa. We exploited a suddenly rich environment using new tools and intense social coordination. Only this time, the environment was not just a recovering grassland. It was the entire biosphere. We planted more. We cleared the forests. We irrigated the deserts. We learned how to hoard energy as grain in silos, as fat on livestock, as fermented foods in jars. We bypassed nature's normal population controls by converting entire landscapes into massive, extended human stomachs. The energy that would have flowed into wild food webs was ruthlessly diverted into human ones. The result was an explosive surge in population. Just like after that ancient climate bottleneck, when a few thousand survivors blossomed into millions. Agriculture allowed a few million scattered foragers to explode into billions of farmers, city dwellers, and industrial workers. It is the exact same story, just played out on a planetary scale. More controlled energy equals more bodies, more complexity, more everything. But there is a catch. You cannot cheat the 10% rule. You can only move the losses around. When we produce industrial meat, we are essentially building giant, machine-assisted herbivores and predators. We grow plants using fossil fuel fertilizers. We feed those plants to animals. We process the animals in massive factories, refrigerate their bodies, ship them across oceans, and cook them with gas or electricity. Every single one of those steps leaks energy. Every step adds another tax. By the time a steak lands on your plate, it drags behind it a long, invisible tail of burned fuel, cleared land, lost biodiversity, and wasted calories. That is exactly why our position in the modern food web is so incredibly heavy on the environment. We are not just another predator sitting quietly at the top of a natural pyramid. We are an apex predator perched on top of a towering artificial mountain of energy that we assembled ourselves. And the planet is paying the bill. When we bulldoze a forest to grow soy just to feed cows, we are flattening a brilliant, multi-layered, wildly complex food web into a crude, two-step funnel. Sunlight to cattle to humans. The thousands of species that used to share that sunlight are gone. The predators that relied on them fade away. The decomposers that recycled them lose their jobs. The entire local energy grid collapses into a single pipe pointed directly at us. Scale that up across continents, and you get the modern world. Vast, sweeping zones of high-intensity human food production feeding massive cities that behave, ecologically speaking, like giant carnivores. Millions of mouths sitting at the top tier, supported by stripped-down, simplified energy pipelines running below them. This is one of the hidden engines driving climate change. We burn fossil fuels to run the tractors, to forge the fertilizers, to pump the irrigation water, to power the processing plants. We dedicate mind-boggling amounts of land just to feed the animals that feed us, losing 90% of the energy at every jump. We let methane bleed into the sky from cattle and rice paddies. We wipe out the forests that used to lock away carbon and catch sunlight in incredibly efficient, complex webs. All of this is just the 10% rule made visible on a planetary scale. Energy moves. Most of it is lost as heat and waste. The more steps we add, the more we burn, the more we waste, and the hotter the planet gets. Understanding this is not just some academic thought experiment. It points directly at what sustainable food choices actually mean in the physical world. Eating lower on the food chain, more plants, fewer animal products, literally deletes an entire trophic level or two. It is not a moral argument. It is a brutal argument about efficiency. Less energy lost between the sun and your stomach means less land, less fertilizer, less water, and fewer emissions. You are not changing the rules of the universe. You are just playing the game closer to the ground, where the math is still in your favor. supporting farming systems that actually mimic ecosystems rather than bulldozing them can rebuild some of that lost complexity. Polyculture, agroforestry, regenerative grazing, more species, tighter nutrient loops, multiple miniature food webs stacked on the exact same piece of land, with humans acting as one participant instead of the only mouth that matters. Even small shifts matter. Trading a few heavy meat meals for plant-centric ones, choosing chicken instead of beef, or eggs instead of a steak. All of it quietly ratchets your personal energy footprint down a rung or two on the web. But there is another possibility glowing on the horizon. A truly wild idea. What if we did not need animals at all to get meat? Lab-grown meat, cultured meat, cellular agriculture, whatever you want to call it, is a desperate attempt to break one of nature's most implicit assumptions, that if you want muscle, you have to build an animal first. Right now, to get a steak, nature forces you to feed a cow for years. You spend massive amounts of energy building bones, a brain, an immune system, hooves, behaviors, an entire living, breathing creature, just to eventually harvest a few cuts of muscle. Cultured meat says, what if we just skip all that? What if we feed the nutrients directly to the muscle cells floating in a bioreactor? No hooves, no horns, no nervous system, no predators, just tissue. In theory, this could bypass some of that brutal 10% loss. Not the foundational thermodynamic losses, of course. You still have to grow plants somewhere to feed those cells. But you cut out a massive chunk of the biological overhead. The walking around the body heat, the reproduction, the immune fights. You are not running an animal, you are running a tightly controlled growth machine. If this technology ever truly matures, it could do something radical to the global food web. It could partially step humans out of the apex predator role, shifting us into something stranger. Direct managers of energy flow. Imagine high-yield crop fields feeding not animals, but stainless steel bioreactors. Imagine oceans slowly filling back up with fish because our endless demand for wild protein simply dropped away. Imagine forests creeping back over the land because we no longer need continents of pasture. Will it work at scale? Nobody really knows yet. The early versions are incredibly power-hungry and wildly expensive. The 10% rule is still lurking in the background, demanding its tax in electricity, steel, and raw materials. Maybe we will just end up trading one set of inefficiencies for another. But the mere fact that we are trying shows just how deeply this simple rule is buried in our future. Even our most sci-fi food technologies are really just wrestling with the exact same fundamental question. How do we move power from the sun into a human body with less waste, fewer steps, and less destruction? From the ancient wind-swept prairies to the glowing modern megalopolis, from the wild wolves to the feedlot cattle, all the way to the hypothetical meat factories of tomorrow, the logic has never changed. Every butcher counter is a decision about exactly where you want to sit on the global energy pyramid, and exactly how much of the world you are willing to burn to keep your seat. Look beyond your plate, beyond the farms and the forests, beyond the planet itself, down to the deepest level where everything you have ever eaten, every predator that has ever stalked the earth, every single leaf on every tree is just the universe's way of rolling energy down a hill. Because that is what this all ultimately comes down to. Thermodynamics. not in the dry textbook sense of equations and symbols, but in the steep, unforgiving reality that every living thing is trapped inside the exact same cosmic accounting system. And the 10% rule. The reason you do not eat lions is just how that accounting looks when it wears the mask of ecology. Here is the heart of it all. The universe has strict rules about energy. You cannot create it, you cannot destroy it. But every single time you use it, every time energy changes hands, a piece of it becomes useless for doing any more work. It bleeds away as heat, as randomness, as what physicists call entropy. Life is the beautiful, desperate art of fighting that drift toward disorder. Temporarily, locally, by burning staggering amounts of energy. A cell has to pump ions, a muscle has to contract, a brain has to fire signals. All of that is power spent pushing back the chaos for just a little bit longer. But the bill for that effort is always the same. You lose a piece of the energy to the cold dark, and you can never, ever get it back. The 10% rule. The fact that only a tiny fraction of power makes it from one trophic level to the next. It is just entropy in a biological disguise. Plants catch the sunlight, but most of that power is spent just keeping the plant breathing. Only a sliver becomes new leaves, roots, seeds, things a herbivore can actually eat. Herbivores do the exact same thing, and so do the carnivores. By the time you reach the apex predator, almost everything has been spent. From the universe's perspective, a meat-eating animal is an absurdly expensive machine designed to take sunlight, run it through multiple chaotic cycles of digestion, movement, and metabolism, and then finally radiate it out into the void of space as body heat. It is beautiful, but it is wildly wasteful. It has to be. That is why there are always fewer predators than prey. That is why predator populations are fragile, jittery, and so easily wiped off the map. And that is why when your ancestors were quietly deciding what was worth hunting, trapping, raising, and feeding, they almost never picked the carnivores. The universe had already made the decision for them. But this is not just a story about early farmers and missing lion steaks. This energetic ladder has shaped life on Earth from the very first spark. Go back billions of years. The earliest organisms were essentially tiny chemical scavengers living on geological energy gradients, feeding off the heat of hydrothermal vents, scraping together whatever simple molecules they could find on a violent, hostile planet. Then photosynthesis evolved, and suddenly the Earth had a brand new way to tap into the cosmic energy budget, the sun. Plants and algae started spinning photons into chemical bonds. They became the massive glowing foundation of almost every food web on the planet. Everything else, directly or indirectly, hitched a ride on that flow of power. Once you have primary producers, the rest of the pyramid is basically inevitable. Organisms will evolve to eat them. Other organisms will evolve to eat those. Predators will appear, and then bigger predators, and then hyper-specialists that only eat very specific prey. But the 10% rule always drags everyone back to reality. The pyramids grow a few stories tall, and then they just stop, because there simply is not enough power left at the top to build another floor. This constraint is burned into the history of life. It limits the size of ecosystems, the number of species they can hold. How massive animals can grow, how many apex predators can patrol a territory at the same time. It shapes evolution itself. Traits that save energy. Better insulation, more efficient. Muscles, smarter. Foraging strategies are richly rewarded. Traits that drain too much power are ruthlessly erased. If you rewound the history of the Earth and played it from the beginning over and over again, the specific cast of characters would change. Maybe no lions, maybe no humans. But you would always get something that looks exactly like the 10% rule. You would always have energy pyramids. You would always have a world where apex predators are rare, expensive, and delicate. And you would always have the exact same underlying logic. Eating predators is a luxury, not a survival strategy. The math simply refuses to work. For almost the entire history of the Earth, every single organism was completely trapped inside this math. You could shuffle around within the rules, become a little more efficient, find a new food source, cooperate, migrate, but you could never step outside the system. Then very recently, and by recently I mean the last few tens of thousands of years, one species started to cheat. Your species. Humans did something no other animal has ever done at scale. We figured out how to tap into flows of energy that we did not biologically evolve to use. Fire let us unlock the calories hiding in foods that would otherwise be barely digestible. The cooking of meat and tough roots effectively gave us more than 10% of what we ate, because we were outsourcing a huge chunk of the digestion process to the flames outside our bodies. Later agriculture let us compress staggering amounts of solar energy into neat, orderly fields of grain and docile herds of herbivores. We were no longer just chasing whatever nature happened to provide. We were actively engineering the base of the pyramid, plowing, irrigating, fertilizing, breeding plants and animals to ensure that the absolute maximum amount of energy ended up in human mouths rather than vanishing into wild ecosystems. And then came the true violent break from the past: fossil fuels. Coal, oil, natural gas. This is just ancient sunlight. Power stored in the crushed bodies of organisms that died hundreds of millions of years ago. When we started burning them, we were no longer just living off this year's harvest of photons. We were draining a planetary savings account that took geological eras to build. Tractors, fertilizers pulled from natural gas refrigerated cargo ships packed with meat. Factory farms, vertical greenhouses glowing in the midnight dark. All of this is just us using fossilized sunlight to bend the ancient 10% rule in our favor. In a natural ecosystem, you can only push so much energy through a food chain before the whole thing collapses under its own weight. In an industrial food system, you can just pour massive amounts of external energy in from the outside and prop the whole thing up. But that magic trick comes with a terrifying bill. You do not escape thermodynamics. You just move the costs around. All that energy we burn to grow chill ship and process our food does not just disappear. It becomes heat, carbon dioxide, nitrogen runoff, collapsing fisheries, blowing topsoil. Locally, we are building a towering artificial pyramid where humans sit as the ultimate apex predator, devouring both plants and animals at scales the Earth has never seen. Globally, the entropy keeps rising, and the planet is absorbing the shock. So here we are, a species smart enough to partially transcend the energetic limits that shaped all life before us, but perhaps not quite smart enough yet to avoid destabilizing the very system that keeps our hearts beating. Which raises a quiet, vital question. What does food look like in a future where we actually take the math of energy seriously? Some of the possibilities are already sitting on the table, quite literally. Plant-rich diets are the most obvious answer. If you eat closer to the base of the pyramid, you waste less power. Fewer steps between the sun and your stomach means fewer losses at every single jump. It does not mean absolutely no animal products ever, but it does mean that the current global norm funneling mountains of grain into animals just so we can eat their meat every single day looks energetically absurd. Then there is the technology trying to rewire the pyramid entirely. Lab-grown meat bypasses the animal and grows muscle cells directly. Insect farming turns low-quality plant waste into dense protein far more efficiently than cows or pigs ever could. Precision fermentation uses microbes as microscopic bioreactors, spinning electricity and simple inputs into fats and proteins. Push it even further, and you get into the truly bizarre. Imagine food systems where sunlight is caught by solar panels, turned into electricity, and then fed as chemical energy into steel vats, where bacteria churn out perfect amino acids and vitamins. No fields, no herds. Just a direct conversion of photons into food through pathways engineered entirely by humans. In a way, it is just us trying to build a better, tighter, less wasteful energy pyramid. Fewer leaks, fewer losses, less entropy pumped into the biosphere for every calorie we consume. But even in the most high-tech sci-fi scenario you can dream up, the exact same rules are still humming in the background. You cannot make energy out of nothing. You cannot recycle it perfectly. You can only choose how you want to spend it and where you are willing to let the waste pile up. That is the philosophical punchline of the 10% rule. It is not just an ecological curiosity. It is a quiet reminder that everything in your life, what you eat, how you live, what kind of civilization you can afford to build, is constrained by math you never voted for. Your ancestors did not sit around a fire calculating trophic yields when they decided to pen up sheep instead of hyenas. They felt the consequences in their empty stomachs, in the survival rates of their children, in the stability of their villages. Predators were rare, dangerous, slow to grow, and wildly expensive to fuel. Herbivores were abundant, predictable, and easily converted into milk, wool labor, and meat. The universe had already done the math. They just followed the results. And that brings us all the way back to our initial mystery. Why don't humans eat meat eaters? The clues were sitting right in front of you the entire time. In the shape of the food webs, in the haunting rarity of apex predators, in the sprawling size of the beef aisle at your grocery store compared to the tiny corner of exotic meats, in the way every ecosystem on Earth thins out the higher you climb. You were not looking at a quirk of human culture. You were looking at the shadow of thermodynamics falling across your dinner plate. Now the question is no longer, why don't we eat lions? You know that answer. The question is something much harder. Now that we understand the energetic rules that built our world, and now that we are powerful enough to bend them, what kind of relationship with food and energy will we choose next? Picture this. You sit down to eat. Nothing dramatic. No Ice Age wind howling outside a cave. No saber-toothed cats prowling in the dark. Just you, a plate of food, maybe a screen glowing softly in front of you. It feels entirely ordinary. But hidden inside that quiet moment is the exact same brutal arithmetic that shaped our ancestors, our empires, and the entire living world. Every bite on your plate is a receipt, not for dollars, but for energy. And the numbers are staggering. That cow, it turned grass into muscle at an efficiency of maybe 10%. The grass turned sunlight into sugar at an efficiency of maybe 1%. By the time that steak reaches you, You are skimming the absolute foam off the top of a massive cascading waterfall of lost energy. And if you were eating a lion instead of a cow, you would be skimming the foam off the foam. Predator on predator dining is like trying to survive on the tips of the tips of the tips in a broken economy. Nature simply refuses to pay that bill. That is the silent revelation behind everything we have talked about. The 10% rule is not just a biological fun fact buried in a textbook. It is the hidden math of your plate. It decided which animals we welcomed into our barns and which ones stayed behind the bars of the zoo. It decided where the first cities could rise, how many people could live inside their walls, which empires could afford to march their armies across continents, and which cultures had enough surplus energy to spare minds for art, science, and philosophy, instead of spending every waking hour chasing down meat that was too expensive to catch. Energy is the invisible currency of history. Our ancestors did not sit down and run the numbers on trophic levels, but their choices were graded by physics anyway. The tribes that tried to live too high up on the food chain, hunting mostly predators, were hammered by the math. Exhausting hunts, scarce prey, unstable returns. One bad winter, and everyone starved. The groups that leaned into the herbivores and the plants who figured out how to harvest the cheaper, heavier energy sitting lower on the pyramid could afford to feed more children, more elders, more specialists. Farmers, potters, blacksmiths, storytellers, priests, scientists. Culture itself is what happens when energy becomes predictable enough that not everyone has to spend every single day hunting for calories. That is the real twist. The 10% rule did not just shape food chains. It sculpted languages, myths, trade routes, and the strategies of war. It is woven into deciding which animals show up in our stories as gods and monsters, and which ones show up roasted on a spit. It is written into religious dietary taboos, tales of famine, and epic migrations. Every civilization that has ever existed has had to negotiate with the exact same unforgiving equation. How high up the ladder can we eat before the energy debt breaks us? And you are still living inside that negotiation. When you choose the chicken over the beef, or the lentils over both, you are quietly walking up and down that energy pyramid. When governments debate land use and climate policy, they are really just arguing over how much of the planet's photosynthetic budget we can afford to set on fire at every step of the food chain. When we talk about sustainable diets, planetary boundaries, and the future of 8 billion humans, we are talking about the 10% rule without ever saying its name. So the next time you look down at your dinner, a burger, a salad, sushi, whatever it is, pause for half a second. Ask yourself, how many steps away from the sun is this? How many losses had to compound to put this on my plate? How many alternate worlds vanished simply because the math of energy said no? Because once you see it, you can never unsee it. Your kitchen transforms into a quiet little battlefield of ecological decisions. Your refrigerator becomes a map of hidden power flows. Civilization shrinks down to something deeply intimate, a fork, a plate, and a humming universe of physics lying just beneath it. If you want to keep exploring these hidden laws that quietly steer your life, the mathematics of energy behind your food, your city, and your species, make sure to hit the like button so YouTube knows to show you more of this kind of journey. Subscribe if you haven't already, and turn on the bell so you do not miss our next deep dive into the secret rules of nature. I would love to hear from you in the comments. Tell me where you are watching from, what country, what city, and how your local food culture fits into this story. What should we explore next? The economics of street food, sacred animals, why some cultures lean so heavily on meat while others do not. Leave your questions and ideas below. So many of our future videos begin right there. And if you want to go even further, you can join our channel membership right here on YouTube. It is entirely optional, but it helps us spend more time on deep research animations and the kind of long-form storytelling that most algorithms do not usually reward. If it is not for you, no worries at all. Just watching, liking, and sharing is already an immense help. Your plate is not just food, it is a condensed history of sunlight evolution and human decision-making.